Hello and welcome to the latest edition of Office Hours by BYK-Gardener. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. If you're unfamiliar with our Office Hours format, let me give you a quick overview. It's typically a shortened presentation, usually 20-25 minutes, followed by Q&A, open discussion, addressing any challenges or questions you have in your own facility or with your color programs. So as you do have questions, or if you have them right now, drop them in the chat and we'll get to them immediately following the presentation. Also note that we are recording this, so immediately following, you'll receive an automated link to the recording. Feel free to listen to it later, grab some screenshots, share it with colleagues, whatever you like there. Also, please note, if you do have a question after the fact, you can simply hit reply to any of the marketing messages you receive. It'll come to my team and we'll route them to the representative in your area or the right technical specialist. Today's presentation is all about controlling color, gloss, and grain texture with the new, well, it's not so new anymore. Fairly new, spectrophotometer, the spectro2profiler. Presenting today, special treat, we have Steve Lay. He is our head of sales. Our usual person, Noah, he's out in the field installing or doing something. So we get Steve today. So Steve, welcome. How you doing today?
Thanks, John. Can you hear me?
Yeah, loud and clear. Loud and clear.
Wonderful. Okay. Well,
take it away.
John. All right, thanks for the introduction. Let's kick this thing off. Thanks everyone for taking some time today to join us. Like John said, we're going to talk today a little bit about a newer solution that we now are able to offer called the spectro2profiler. And before we get started, I'll just lay out a little bit of what we'll be reviewing today. First off, we'll talk about why we thought this was a good solution and why we think it can solve some problems that some customers are having. And then we'll delve into a little bit about how it works, some of the measurement principles behind what's baked into the instrument. And then we'll look at some samples or examples of material that you might measure with this instrument, and then look at the data that the instrument that can produce and see how that correlates to the visual. And then after that, we'll do a little Q&A like John mentioned. So that said, let's start this thing. So maybe you know a little bit about BYK-Gardener instruments and maybe you know a little bit more, but what customers come to BYK-Gardener when they want to measure what they see. And historically, we've been really good at providing that capability, whether a customer is developing a product or they have a control or a standard that they want to measure against their product, or they're in production. If they want to measure what they see, we've been really successful in helping customers in that regard. Historically, they've come to us to measure color through our line of spectrophotometers. They've come to us to measure gloss through our very robust and reliable line of gloss meters. But through the years and through seeing different applications and different customer concerns, we've learned that customers that have surface structure or texture or topography to their material, the color and gloss doesn't always tell the full story in terms of how we see it or how we visually perceive it. So that's where we thought that coming out with an instrument that took that into consideration would be helpful to customers. So what we did was combine multiple measurement techniques into one instrument. So in this instrument, there's a lot going on. And like I said earlier, we're going to talk about what the instrument is actually doing and how it's coming up with the data that it provides. So over the next few slides, let's buckle our seatbelts as we get into that. So let's see here. First off, built into the instrument is a spectrophotometer. It's configured like our handheld unit, the Spectro2 Guide. So it comes with all of the features that any reputable spectrophotometer on the market has, all of the standardized illuminance, the different color difference equations and color systems. And the geometry of the spectrophotometer built into this instrument is 45-0, which just means that the specular data is excluded from the colorimetric data that the instrument provides. And it has a circumferential illumination, like we see here in the picture, an illumination every 60 degrees, and then with a detector at 0. The reason it's 45-0 geometry is because we want, again, to measure what we are seeing and like we are seeing. So when we have a 45-0 configuration, the gloss or the texture is irrelevant. It's going to give us colorimetric data that correlates to what we're seeing. So that's the first component, or that's built into this technology. The next is an actual gloss meter. So it does have a 60-degree gloss meter built into it for legacy data purposes, to give the ability to correlate to international standards. However, we do know that folks that are using this instrument or have the potential to use this instrument are probably going to be using it on surfaces or material that have some texture or topography to them. And when you use a standardized gloss meter with its 60 or 20 or 85-degree illumination, and that illumination is coming in from one of the sides, it's going to more than likely cast shadows and falsify your results and create these shadow zones, which is going to create inconsistencies and really hurt the repeatability of your data, and also take into account how the instrument is configured. Maybe every operator configures the instrument differently as you present your material to the instrument. So those are all factors that make 60-degree or standardized gloss geometries not your best bet when you're trying to measure textured surfaces. So to address that, the instrument has what we call 2D reflectivity measurement capability built into it. And with this, we now have an inline illumination and detection set up. So we have a camera set up on top, and using a beam splitter, the illumination is directed in the same direction as this detector or camera. So this helps eliminate those shadow zones, and because now we're illuminating and detecting from 0 degrees. So since we use a camera, we get these spatially resolved reflectivity measurements. So in other words, we are we're getting a picture that has pixels, and every pixel has a certain reflectivity value. What we see here is a reflectivity map of a powder-coated surface. And the black pixels are showing us where we have low reflectance or reflectivity areas, and the brighter it gets, or the silver areas, are showing higher reflectivities on the surface that we're measuring. So the measurement area on the instrument is going to be 15 millimeter by 15 millimeter, and there's a resolution of 512 by 512 pixels. So if we take all of those reflectivity pixels values and average them, in this example, we're going to get about 11,500 on a scale of 0 to 500,000. So the reason this is important or potentially helpful is the resolution, right? Because if you think about it from a gloss meter perspective, more times than not, you're talking about a range of 0 to 100. But when you factor in 0 to 500,000, that will allow you to more accurately characterize the reflectivity of a given textured surface. And then finally, the final capability built into this instrument is that 3D topography measurement. And to get this 3D information, the instrument uses what's called photometric stereo technique. And how that works is when an object, in this case, material or the surface that you're measuring, when that material gets illuminated from different directions, it's going to cast shadows. And in this case, shadows are a good thing because it's helping us determine a height map. And based on those shadows and the shape from the shading from those shadows, we can then estimate a surface curvature and then calculate the height map from that surface curvature. And here is what that setup looks like. We've got 4 light sources that are used illuminating at 60 degrees, positioned every 90 degrees. And then the height map has a resolution of 1 to 2 microns. So all of that capability and technology is built into this new instrument for us. Some folks are using it as they see fit. Maybe they purchased it to use it mostly as a color instrument. They can use it as a standalone gloss instrument, and maybe sometimes they have some texture that they want to measure and characterize, and they can use it for that. So you can customize the data to show whatever it is you want to see at any given time using the smart chart software that accompanies the instrument. So that's a little bit about the setup and how it works. The setup and what the capabilities are and the theory behind it. So let's now delve into a little bit of examples. So when R&D was developing this instrument, they were thinking about who could benefit most from this technology. Who can we market this to, and how can it help those folks? So obviously, car interior came to mind, like seats and dashboards and center consoles and the ceilings. Those are all colored, textured materials that a lot of times have to be uniform in order to have a successful product. So that's one algorithm that's built into the instrument, and each one of these algorithms has a number of different scales that help us characterize the product that we're measuring. So for today's purposes, like John mentioned, this is a shortened presentation. We're not going to go through each algorithm, but for today's purposes, we'll run through some of the scales on the leather-like algorithm. But we do know that there are other applications, like in coatings, for example, a powder coating textured application where this instrument could be helpful, as well as plastic parts or textured paint, where we might use the fine algorithm. So let's jump into this leather-like algorithm for a moment. So here we have an example of 3 different slushes or skins, for lack of a better term, that all kind of look the same, but at the same time, they don't really look the same, right? They have a different color or shade to them. Maybe the grain looks a little bit different in size or height. Who knows? But we want maybe to be able to characterize that numerically and be able to differentiate between the 3. So how do we do that, right? We've got maybe difference in grain size, difference in height. So what we can now do is determine the cell size or grain size, however you want to call it, and also look at the amplitude or the height of the grain, and then be able to compare each skin to one another. So how the instrument determines these cells is through what we call this watershed segmentation. And how that works is if we just assume or imagine that water falls onto the surface that we're going to measure. And as that water builds in the valleys of our topography, that water builds, and whenever a river completely surrounds a hill or a high point, that's going to be what the instrument will define as a cell. So here's a graph of what that kind of looks like. And as we move to the next slide, we can see on the left, we have some raw data of a topography of a material that was measured. It's all in grayscale. But then when you add in this watershed segmentation, all of the cells are divided by that green line. So we can not only determine the amount of cells or the number of cells in the measurement that we took, but also the size of each, and then the average or the mean size of the cells that of the material that we just measured. So now, if we apply that mean cell size scale to those three slushes or skins that we looked at in the beginning, we can now very easily differentiate between one another based on the numeric values that the instrument provides. So sample 1 has a smaller cell size than does sample 2, but then sample 3 has the smallest. So that would be one way that we could differentiate very easily differentiate between those three samples using this instrument. So the next scale in this leather-like algorithm is cell amplitude. And here we have a plaque that has 1, 2, 3, 4, 5 different depths, right? We've got the 100% depth, which is probably the most rigid and the most outstanding and most prominent. And then it kind of tapers off from 80 to 60 to 40 to 20, which is more of a flat, less noticeable grain or rigid texture. So how can we characterize that? How can we put numeric values to that? So what the instrument will do is first detect the cells like it did earlier, and then determine in each cell what the maximum point is, the high point in each cell, and then also determine what the minimum point is in each cell, and then subtract that minimum value from the max, and then give us an amplitude value. And then you can get that an average value of amplitude from the sample that we measured, again, allowing us to differentiate one from the other. We can see here that the 100% depth part of the plaque has a value of 150 for amplitude microns. And then we gradually make our way down to that 20% depth where we have a value of close to 60 microns. So this, again, makes it very easy for us to numerically differentiate between the depth of a particular grain in a product or a sample that we measured. So this last example that I'll share is what makes, I think, the instrument stand out from anything else on the market. Now, how often this is applicable in the marketplace, I don't know, but the technology is pretty cool, and it's worth talking about. So here we have 4 skins similar to the last example, but these really don't look all that different from one another like the last example did, right? The texture size, the cell size is very, very similar to one another throughout the 4 examples. And maybe the gloss and the reflectivity overall, if you were to use a gloss meter, is very, very similar from one another. So what's different about it? You can see something. I'm not sure if it's translating over a virtual presentation or on the slides, but there is something different about how they appear visually. And basically what it is reflectivity contrast. And what that means is even though the cell sizes are the same or very similar, and maybe the amplitude and the depth is the same, we have a difference in reflectivity from the peaks of the texture versus the valleys. And that reflectivity contrast is what's causing the visual difference. So on the left here, we can see topography data, so 3D data that the instrument provides. And on the right, we see the 2D reflectivity data that the instrument also provides. But since we measure with the same optics, we can now align and overlay the data. And then we can calculate the contrast between the hills, the peaks, and the valleys, the low points. So we now have this value called RC, reflectivity contrast. It's taking all of that into consideration and giving us one easy to understand numeric value. So if we take that simple equation and plug it into this RC value, we can now see that sample 1 and sample 3 appear to be more similar to one another from a RC perspective, and that's where we're seeing the differences. 2 and 4 are more similar based on that reflectivity contrast. So this is the impressive part of the instrument, where it takes into consideration not only color, not only gloss and reflectivity, not only 3D and texture, but it really does combine all of those technologies and needs from a visual characterization perspective and put them into numeric values that are easy to understand. So I mentioned the software earlier in the presentation, and the instrument can be used as a standalone instrument. It's a mobile, portable instrument that can be taken off-site with data collected and bring it back and plug it into the software, or it could always be used as a standalone instrument where you just read the data off of the screen. But when you combine it with the capabilities of the software, you're able to do many more things, like create tolerancing, for example, create what we call digital standards. You can also take a measurement, for example, in the leather-like algorithm, and then very easily switch that measurement data that you collected to the coarse paint algorithm or the fine texture algorithm with the click of a button. So you don't have to necessarily remeasure if you wanted to measure under a different algorithm. So those are just a few of the benefits of the software, but it works really well in concert with the software, but it also works as a standalone instrument as well. So here gives you an idea of maybe some of the real estate that you might need on your material to measure for each one of these capabilities. The aperture is, I think, 25 millimeters circular aperture. But you can see here the respective areas that you would need to measure each one of those components. So that wraps up our short presentation, and I think I'll hand it back over to John to conduct the Q&A session.
Yeah, thanks, Steve. This was great. And I love this instrument. It's just so versatile, and the fact that it does the texture and has the 3 varying coarsenesses. And, I'm glad you wrapped up with the software at the end, because that really ties it all together and gives you, exponential power there. On the screen, you see Noah's email address. He's one of our technical specialists. Feel free to email him directly if you have questions, beyond this. But we have some time left, so if anybody has some more questions, drop them in the chat, and we'll get to them. One thing I'm going to add to the chat, I just dropped a link in there. There's an article on 2D, 3D surface texture measurement that we have on our website that's worth a read. So take a look there. Steve, in your experience in working with customers looking to measure grain and texture, what are the, I guess, where would someone start this process if they want to actually measure and control grain?
Sure. So I'd say a general rule of thumb, and this is no pun intended, a general rule of thumb is that if you rub your thumb along your material and you can feel something, then this instrument will be able to characterize that, whether it be in the 3D realm. So if you have product that's exhibiting that where you can feel it actually with your finger, then it might be worth considering this instrument if you have a need to differentiate between good and bad product, or remain consistent throughout a batch or a run. So that would be my first recommendation in thinking about considering this type of technology. The next is what we found successful is trial. You don't know what you don't know until you try. And since this technology is somewhat new, some customers that we've worked with have been comparing this capability with the way they've done it historically, whether it be with a profilometer or some other type of more expensive or more intricate technology. And maybe they want to compare the values they get with this instrument to the way they've always characterized this type of material, which is always something that we can help with. We can do it in one of two ways. We have regional salespeople that cover all of North America that have these instruments in demo stock and can come by and do this presentation for your team, and also run through some product and take measurements and discuss the data that are a result of that trial. Or we've also lent the instrument out to folks for a week or two or three and let them work with it and take measurements on their product. And then we circle back on a Teams meeting to discuss the data and look at trends and discuss any questions, open-ended questions that are a result of the trial. So that's typically how we've worked this instrument in with our customer base.
Cool. I mean, question just popped up here. How does the output compare to a profilometer roughness or the various paint orange peel outputs?
Well, it's not really going to be a good indicator of orange peel. We have a different instrument that will measure orange peel. Typically with orange peel, getting back to my thumb reference, you can't feel the orange peel when you run your thumb against it in most cases. So I don't know that this would be the best instrument for that type of application, but it's always worth a try. We have had instances where you couldn't feel anything with your thumb, but the instrument was providing numeric data for the 3D topography scale. So I always, if you have interest or you're interested in seeing how it compares to, again, a profilometer or your data that was provided to you via your profilometer, it's worth a try to see it so that you can compare for yourself.
Yeah, you're right. The best is just to test with your specific application and see what the data looks like, see how we can, use that for reporting for, enhanced quality control. So good stuff. Another question here, reflectivity contrast. Would you mind touching on that again in maybe a little bit more detail? Shout out to Maggie on that one. Good question, Maggie.
Sure. So here's back to that slide, right? So we've got, it's all about measuring what we see. We want to be able to characterize what it is that we're seeing. And if you were to measure these with a gloss meter or a spectrophotometer, you probably would not get very much differentiation, even though there is some visual difference between the four skins. So the reason for that, the reason that we see that is not because of a color difference, not because of a gloss difference. It's because the peaks of this texture have a different reflectivity value than do the valleys. And that's causing our eyes to perceive each skin different. So what the instrument is able to do is characterize the reflectivity on the peaks and then compare that reflectivity to the reflectivity of the valleys. And then through this equation that we see on the screen here, give us one numeric value that represents that difference. And that's, in this case, what's causing the visual difference is the contrast in reflectivity between the peaks and the valleys.
Cool. Maggie, did that answer your question? Feel free to jot in the chat, or if you need something else elaborated. Thank you. In your experience, Steve, what are some of the unique uses that you've seen customers measuring? I mean, the usual stuff: leather textiles, automotive dashboards, consumer electronics, things like that. But have you seen other successes and kind of some different industries or applications?
Two of them were maybe outside the box applications that I've seen are release paper. That's one. There's a textured release paper that are now customers of ours for this particular instrument, as well as battery manufacturers. So we have a customer using the instrument to characterize how well battery coating coats a cell inside a battery. So there's been some interest in renewable energy from in regards to this technology.
Wow, that's a new one I haven't heard of or even thought of. But there's texture on the inside of like the battery housings that
on the cells,
need to be on the
Yep.
cells. Okay,
because they get there's a coating that goes on the cells, and they want to characterize how well it adheres to the cell.
Nice. How compared to our normal spectros, how does this calibrate? Is it a similar process, or how often would someone need to calibrate this if they're on a line somewhere?
Sure. So the instrument uses LED as its light source. So this light source is very stable. It's not typically prone to falling out of calibration if you were to take it from a temperature controlled environment to a day outside like today where it's 100 degrees. It's not going to fall out of calibration if that happens due to the LED. The LEDs also help in terms of inter-instrument agreement. So one of these instruments is going to measure very, very similar as than would another instrument due to the LED light source. That said, to answer your question, it's a very simple calibration process, just like you would self-calibrate a spectro. It would just ask you to measure a white tile. And then there's also a color and gloss check tile as well that sometimes periodically the instrument will ask you to perform just to make sure that it's reading the way that it should. Okay,
cool. All right, here's a good question for you as we continually play Stump the Steve. We're a paper manufacturer that embosses paper products with various linen, stipple, and finer patterns, typically on low gloss, less than 5 gloss 60. Which surface structure setting would you recommend? Is there a way to directly compare surface test results or as a ratio to the perfect negative pattern that an embossing roll surface represents? Let me read that again.
Sure.
Paper manufacturer that embosses paper products with various patterns like stipple, linen, and finer patterns, typically on low gloss, less than 5 gloss 60 surface. Which surface structure settings would you recommend? And is there a way to compare paper surface test results as a ratio to the perfect negative pattern that you'll see on an embossing roll?
I think I can answer the first part of the question. The second part we may have to circle back on.
Sure.
The first part, again, is really just a trial and error. I would recommend you measure under all of the algorithms and then see which of the scales within all of those algorithms are giving you the best data. So the best differentiating data, or the best data that correlates to what you're seeing visually. And that's the beauty of using the software. You just take one measurement and then you can see all of the scales and all of the different algorithms, and you can pick and choose and customize what you see based on your material and the data that your material is providing. The second part of that question, I would have to do some research on or consult a product manager. Yep.
Sounds good. Roger, we'll get back to you on that and make sure you get an answer. But I mean, to your point, Steve, I think it's just trial and error. Test it out on actual real world samples that you're working with every day. Let's look at the data and see how we can improve your overall process to, you know, reduce scrap and improve your output. I think that's the best way. Other questions, keep them coming in here, folks. We got a lot of time left here. Aperture size, you covered that, Steve. Maybe just touch on that again. How small can this go down to?
Yeah. So it's a 25 millimeter aperture. It's a circle aperture. But here on this slide, it shows you what you would need for the 3D, the 60-degree gloss, and the 2D reflectivity in terms of real estate or material size to measure.
Mm-hmm.
And curved is not probably the best to present to the instrument. You have to cover the aperture completely. No ambient light can get in, or else it won't allow you to take a measurement. Excuse me.
Yeah. No, good. Question here: can it map and provide 2D or 3D texture imaging?
Yes, on the software. Yep, on the software, there's a feature that allows you to view a graphic image of your texture.
Okay.
Is on a grid that shows size and shows depth and micron value.
And the software is our standard smart chart. Is that right? That this plugs into?
That's right. Mm-hmm.
So then, with the reporting capabilities, are customers able to export that 3D or 2D map, or somehow extract that for, you know, in their own internal reporting and verifications?
Yes, there is a report feature that allows you to export onto a PDF report.
Okay, that's cool.
Or print out.
Yep. Good. Let's see. What other things do you run into with folks when they're getting into texture measurement and using the instrument? Are there any tips and tricks you can help folks out there? Put you on the spot there.
Well, other than having the right type of material and material that's going to be able to be presented to the aperture.
Yeah.
I don't really have any other tricks.
I mean, it's like all of our instrumentation.
Yeah.
You set your process to ensure, and the way the instrument's held from shift to shift, from plant to plant, because then you're going to get that true apples to apples comparison. That's right. It seems like we talk about that in every webinar and every training thing we do. That seems to be the biggest issue. If operator A is holding it or doing the measurements one way, and then operator B, across town or somewhere else is doing it slightly differently, you're going to get those inconsistencies in the numbers. What else? Other questions, folks? Just drop them in the chat. We got some time here. We also have some of our regional sales folks on the call. So Steve, you got backup. You're good.
Good to know.
What else? Is that it, folks? We'll give it another minute, see if anyone has questions. We had a good run there. But I assume, metal, plastics, textile, of course. Are there ceramic, or did we get into any, thing like that?
Yeah, anything with texture on it.
Yeah.
It probably has to be opaque, right? Because we're illuminating the surface, so we don't want light to escape through the other side of the material. So opaque material is certainly preferred.
Awesome. Well, folks, I'm not going to keep you. We're all busy and have things to do. If nobody else has any other questions, you can get 20 minutes of your day back there. I think everyone's cheering silently. So thanks for attending. Thank you for joining us. We'll look forward to seeing you on future BYK-Gardener, either web seminars, the 60 minutes format, or this shortened office hours format where it's a little more interactive. Thank you, Steve, for stepping up and stepping in here and taking care of the Spectro2 Profiler webinar for us. I appreciate it.
Thanks for organizing, John. Appreciate the help.
You bet. Have a great rest of your day, everyone. Talk to you soon.
Bye.